our first speaker for this session, Jakob Palmkvist. He is a senior lecturer at Orebro University, Sweden. His presentation will focus on the topic of generalized vector fields. Please welcome, dear Jakob.
Yeah, thank you very much, and thanks a lot for the invitation. Yeah, so as you can see, the title is just generalized vector fields. What I will talk about is some construction of Lie superalgebras of vector fields, which also can be applied in other cases. You can also construct other Lie superalgebras, and in that sense, they can be considered as Lie superalgebras consisting of generalized vector fields in some sense. So this also includes tensor hierarchy algebras, a type of Lie superalgebras that I've been working on for many years, much in progress with Martin Sedoval. So this talk is based on work with him, mainly a paper that appeared last year, and also some work in progress. So I will consider Z-graded Lie superalgebras. I will use capital G for a Z-graded Lie superalgebra over some field K, algebraically closed, characteristic 0. You can think of it as a complex numbers or even real numbers for most of my talk. And I denote the bracket like this. You will see y in a while. And also some more notation before I really get started. When I write G subscript J plus, for example, it means the sum of all subspaces from degree J and above. And also I use subscript on homogeneous elements to indicate their Z degree. So we have a Z-graded Lie superalgebra. One subspace for each integer. If we now forget the subspaces at degree +2 and above, or -2 and below, so we only have 0 ± 1, then we get what is called a local Lie superalgebra, the local part of the original Z-graded Lie superalgebra. So this is in the terminology of Katz. Introduced this in his paper in 1968 when this was part of how Katz-Moody algebras came about, and also generalized to Lie superalgebras in this paper from 1977. So it has nothing to do with locality in other respects. And I use this notation here, the G with an L like this as a superscript. So it's actually not an algebra. Local Lie superalgebra is not an algebra because the bracket is not defined for any pair of elements. If you take two elements at degree +1 or two elements at degree -1, the bracket is just not defined. It's not 0, it's not even defined. So suppose that you have such a local Lie superalgebra. And suppose that it's equipped not only with the bracket, but also with a bilinear map from G-1 cross G1 to K, which is homogeneous with respect to the Z2 grading, and also invariant with respect to the adjoint action of G0, like this. And suppose also that there is a grading element, an element that I denote by L at degree 0, for which the other elements are eigenvectors with respect to the adjoint action with the Z degree as their eigenvalue. So such a structure I will call a contragradient local Lie superalgebra. And any such structure gives rise to a Z-graded algebra that I denote by G gamma. So it's not a Lie superalgebra, it's a Z-graded algebra. It's not associative either, but almost associative, as you will see. So it has a Z grading, and its non-negative and non-positive parts are defined like this. We start with the free algebras of G ±1. We take the direct sum with G0, and then we can consider that as a Lie superalgebra with where the bracket between G0 and this free Lie superalgebra is induced by the bracket between G0 and G plus minus 1 and the Jakob identity. So all this is a Lie superalgebra, and then you can take the universal enveloping algebra of that. And then it's easy to see that you can write any element here as a product of some element in the universal enveloping algebra of G0, and then the tensor algebra of G plus minus 1, since you take the universal enveloping algebra of a free Lie superalgebra. And you can write it in either way. You can move things around using the brackets. You can have a product of elements in G plus minus 1 either to the left or to the right. And so far, this is not an algebra. This is a vector space with a product defined for any pair of elements which has both non-positive degree or both non-negative degree. So far, I have not said how to multiply two elements, one at a positive degree and one at a negative degree. So this I will describe now. So if you consider two elements at a positive and a negative degree like this, we can always write them in this form, so that small x and y are elements in G plus minus 1, and capital X, Y are elements in this tensor algebra times universal enveloping algebra with G0. So we can, when we consider such a product, we can always write them so that small x and y comes next to each other, and then the rule is to first multiply them according to the relations here, using the bracket and this bilinear form that we have. So now we have, so this takes us back to G0, these relations here. So now we actually have an algebra with a product defined for any pair of elements. So the question is if it's associative. And it's associative at non-negative part or non-negative part, as we defined it using this enveloping algebra. And more generally, if we consider this associative law, this holds when x and y both are as non-negative degree or non-positive degree, or when it holds for y, z, but not in general. Not if, say, x has a positive degree, y negative, and z positive again, then this associative law does not hold in general. So we can take an example to see why this construction is useful. So let's take a Lie algebra case, actually. So with trivial odd parts, G is just SL n plus 1, decomposed with respect to GLN. So then the Z grading is just a 3 grading from the beginning. So degree 0 is GLN, and then at degrees plus minus 1, we have n-dimensional fundamental modules of GLN. And they introduce basis elements for these modules like this, where A, B are indices that take n values. And I write them up and down to emphasize that they are dual to each other, these modules. And we have these bracket relations in SLN plus 1. And if we take the trace here of GLN K, if you take its negative, we get this such a grading element L. And we also have, if we take, we have a bilinear form FB with EA is delta AB, chronically delta. So this shows that we actually have what I call contragradient local Lie superalgebra. So then we can apply this construction. So then the question is what this product is. And also, I should say that in this case, of course, the local part of the original Z-graded Lie superalgebra is the same as a vector space. It just means that we forget these brackets, which are 0 anyway. So now we can compute the product of an F with an E in both ways. So we just apply what I wrote on the previous slide. Insert what this is, and we get that FA-EB is KAB, and EB-FA is also KAB plus delta BA. And if we take the commutator here, the difference between these two, then we just get delta. And you see here I used the ordinary brackets for the commutator. So that's why I had this other notation, because it's important now to distinguish. These double brackets are the abstract brackets that I start with, and these ordinary brackets are really commutator. But if we take degree 0 with something, then the two brackets coincide, but not when I take degree +1 with degree -1. And as I said, it's not fully associative, so let's check this. If we take this associator and just insert what we have here for FA-EB and here EB-FC, and we can use the commutator, which is the usual bracket in this case, just to move F to the left. We will come to this thing here, and we can write that KAB is FA-EB, and the same here. And at this point, we actually have associativity where all the F's are to the left and E to the right. So here we can move the parentheses, and then this is what we get. And this is, in general, not 0 in this algebra. But we may factor out this commutator. And then we will be left actually with an associative algebra, which is the Weil algebra with 2 n generators, E and F. So I think this is interesting that we have some non-associative algebra, and you can factor out this ideal and get the Weil algebra from it. And it would be interesting, this is an open question. I will come back to it to the end, but I don't know, in general, if you start with some more general control gradient local Lie superalgebra and take the ideal generated by not the full commutators at degree ±2, but the leading irreducible part of it. And so the question is this ideal proper in general? Can you factor it out and get some kind of generalized non-associative Weil algebra or Clifford algebra in the case where you have a consistent Z grading? So I think this would be an interesting question that I will come back to. So we saw that this big algebra G gamma that we construct, it is in general not associative, but nevertheless it's associative, sufficiently associative for this local part to be a local Lie superalgebra under the commutator. So we get back, we started with some local Lie superalgebra, and then we construct this algebra G gamma, where we take the commutator on the local part, and we get back another local Lie superalgebra. And whenever we have a local Lie superalgebra, we also have a Z-graded Lie superalgebra which is just freely generated on positive degrees and negative degrees. So this is also a result by Katz that whenever we have a local Lie superalgebra, there is this. Katz calls it the maximal Z-graded Lie superalgebra with that given local part. And from that, you can factor out the maximal graded ideal intersecting the local part trivially, and then you get the minimal one. And we can do something similar here, but first we take this maximal one. We take the subalgebra generated by elements at degree -1, which are products of elements in G-1 and G0, and also generated by elements at degree 1. And then we factor out the maximal Z-graded ideal intersecting the degree 0 component trivially. And we call the result the cartonification of G, because you will see that this will produce Lie superalgebras of carton type in some cases. And they also use this notation GW. So we can get back to this example that we looked at before, where G is SLn plus 1 with this 3 grading. And then the question is, what is then this cartonification? What do we get in at degree -1 there? So we should first take all the products of elements at degree -1 and 0, so elements of this form. And the question is, what should we factor out from that? We should factor out as much as possible in some sense, everything that gives 0 when you take the bracket with everything at level or degree +1. So if you take this commutator, so at this point you again have, at this level you have associativity, so you can use the Leibniz rule here, and you will see that this commutator is symmetric in these upper indices B and C. So it means that only the part of this which is symmetric in upper indices survives. The anti-symmetric part is what generates this ideal that you factor out in the construction. So it follows that in this cartonification you have degree +1 and 0 is just what I have here, the G1 and G0 that you started with. But then at degree -1, you have something which is symmetric in the two upper indices and one index down that doesn't speak to the indices up. And you can continue to degree -2 and -3 and so on. You will see that you get more and more symmetric indices upstairs. And this, in fact, is the Lie algebra Wn of polynomial vector fields. So, so far in this example we only had the Lie algebra with Lie superalgebra with an odd, trivial odd part. So since this is a conference about Lie superalgebras, we should go to the genuine Lie superalgebra. So let's consider instead SLn/1. So we have the same as vector spaces, the same subspaces at degree 1, 0, and -1, but now we have a consistent Z-grading, meaning that we have odd elements at odd levels, +1 and -1, and even elements at the even degree 0. So we can redo everything that I did in the previous example. There were a lot of signs will change, and in particular, if we now compute what we have at degree -1 in this cartonification, we will find that there is a minus sign here instead. So we get something at degree -1, which is antisymmetric in the two indices. And if we continue to degree -2, -3, and so on, there will be more and more antisymmetric indices up and then one index down. And then you recognize this as the Lie superalgebra Wn within parentheses. So this is a finite dimension Lie algebra because you have fully antisymmetric indices up. At some point there will be, you cannot have more than n indices and then it stops. So this is included in the classification of simple finite dimensional Lie superalgebras that we got a nice overview of in the previous talk. And there we also saw that this is one of these, so one of the classes in this classification is Lie superalgebras of Cartan type. So this is one of them, Wn. And of course, this is why I call it Cartanification, because we start with this Lie superalgebra, which belongs to another class. This was one of the basic Lie superalgebras, if you remember from the previous talk. And then we apply this Cartanification, and we end up with Lie superalgebra of Cartan type. And this basic one that we started with, it has a Dinkin diagram. So all the basic ones have. But as in view of this construction, as you can see, in some sense, you can consider this Dinkin diagram also as a Dinkin diagram of Wn. So it's just the Dinkin diagram of an-1 or SLN, and then you attach a gray node in the end. So it's also called A0 n-1 because you have 0 nodes on one side of the gray node and n-1 on the other side. So the gray node in the end here corresponds to the isotropic odd simple root that you have. So this construction that I told you about now is something very general, but I will now specialize it a bit and consider cases that are similar to the example that I showed here, in the sense that we can visualize it by a Dinkin diagram. You start with a Dinkin diagram of some simple finite dimension Lie algebra, and then you extend it to Lie superalgebra by attaching a gray node somewhere. So we consider a triple G lambda kappa consisting of a simple finite dimension Lie algebra G, dominant integral weight of G that I call lambda. So in this example that I have here to the left, G is a(n-1), and lambda is the fundamental weight associated to node 1 here, because that's the one that the gray node is attached to. And we let kappa be an invariant symmetric bilinear form on G, so it's fixed up to an overall normalization. So for any such triple, there is a consistently Z-graded Lie superalgebra. In fact, the Borcherdt's Kac-Moody algebra that I denote by B, where the subalgebra degree 0 is the direct sum of G and one-dimensional subspace spanned by such a grading element L. At degree -1, we have highest weight G module with highest weight lambda. So I use this notation for that, or lambda. And then on degree +1, you have its dual, the lowest weight G module with lowest weight minus lambda. Because this is a contragradient Lie superalgebra, so it's any G module that you have on degree P is the dual of the one at degree -P. And then at degree -2, you have what you get if you take the symmetric product of this module at degree -1. So I use this wedge symbol upside down for the symmetric product. And then you remove the leading part, the big representation with highest weight 2 lambda that you know is always present in this symmetric tensor product. And then the dual of V-2 at degree +2. And also if you, see, I mean, you can extend the G to such a Borcherdt's Kac-Moody algebra, and you can also construct it from a Cartan matrix, where you take the Cartan matrix of G, you add one more row and column corresponding to this gray node that you add, and this additional row and column will have a 0 entry in their intersection in the corner of the Cartan matrix, and then apart from that corner you will have lambda in the additional column in the Cartan matrix. And the kappa you can extend to an invariant symmetric bilinear form on the whole of B, and then you can restrict it again to these subspaces at degree ±1. So then you really have the contragradient local Lie superalgebra. If you remember, I mean, this is local Lie superalgebra where you, apart from the bracket, also have such a bilinear form and a grading element, but this you also saw that we had. And then you can apply this construction that I described, and we get this cartonification BW. And as I described, what we do then is, I mean, first we construct this big algebra that I call B lambda, which is not fully associative, but almost. And then we consider it, we take its local part, we take commutators, and then we take the subalgebra generated by products B-1, B0, and B1, and then we factor out the maximal graded ideal intersecting B gamma 0 trivially. But now in this construction, we can replace B0 by some subalgebra of B0 and modify this construction a bit. So we can take what I call here G minus instead. So let G minus be the subalgebra of G obtained by removing all nodes such that the corresponding Dinkel label is non-zero. So it means that we, you remove the nodes, the white nodes that are connected to the gray one. You only keep the other ones. So in this case, the example that we saw before, where G is AR and lambda is capital lambda 1, G minus is AR minus 1. And then by replacing B1, B0 with B1, G minus in this construction, we get some modified cartonification, which I call strong cartonification. So the other one is the weak. So if we take this example again, the Lie superalgebra case, where G lambda is AR and capital lambda 1. So then you get SLN/1 if R is n minus 1. And you take kappa to be given by kappa of EI and FI equal to 1 for all for all generators EI and FI. So this is a natural choice that you can have if you have a simply laced Lie algebra G that you start with, then this is the natural choice for kappa. So this will always be assumed also in the rest of my talk when I have simply laced G. So then if you apply this construction, as I showed before, as BW, you get the Cartan Lie superalgebra WN, but the strong cartonification now gives SN, which is also a Lie superalgebra of Cartan type. So if you think of the ordinary WN as consisting of vector fields with odd coordinates, then Sn is a subalgebra consisting of divergence-free vector fields. So this is also why I call it strong and weak cartonification. I mean, originally these letters S and W, originally they don't mean strong and weak, but I think it could fit well with that. So now we can take the other class of simply laced classical Lie algebras. So we take G to be dr for some R. And again, lambda equal to capital lambda 1. So the gray node is attached to the node in the end of the Dinkel diagram of dr, further away from the branching. So then you will see that the weak cartonification is the contact Lie superalgebra K1/2R, and the strong cartonification is the Hamiltonian Lie superalgebra H 2R. So this is also included in the finite dimensional Lie superalgebras of Cartan type. So this one, the contact Lie superalgebra, is not finite dimensional, but it grows linearly, so you still have control over it. But also in many cases, well, in most cases, you get something infinite dimensional when you apply this construction. And there are also other algebras that you can get by a similar modification of the original construction by restricting B1, B0 even more. So for example, the Lie superalgebra Pn, you can get from this Dinkin diagram and then restrict to this subalgebra. The infinite dimensional E5,10 is associated to this Dinkin diagram. So this was an observation made by Martin a couple of years ago. And then we also come to the E series. I mean, I talked now about the A and D series of Lie algebras. So then it's also interesting, maybe this is the most interesting case also from the point of view of the applications to physics that I will come to. What happens if G is E6, E7, E8, or even you can take other algebras in these E series. So I always have a Dinkin diagram like this. So lambda is always capital lambda 1 with respect to this Dinkin diagram. So the gray node is always associated attached to the white node in this end of the diagram. And I can also include E5 and E4, but that's just the same as D5 and A4. So then we'll see something remarkable. Up to r equals to 7, there is symmetry around z degree 9 minus r divided by 2 in this strong Cartanification. And you can see it here in an example. This is for r equals to 7. So here we have, I just written down the dimensions of the subspaces that you get. So you have E7 as a subalgebra at degree 0. And then you have E7 modules. So in B, which is a contragradient Lie superalgebra, you always have this symmetry around level 0 because it's contragradient. The module at degree P is dual to the one at degree minus P. So the one that you get by this Cartanification is not contragradient in general. So there is not this symmetry around degree 0, but as you can see, there is this other symmetry, which is around degree 1 in this case, because now if I take r equals to 7, I get 1 here. So this is quite remarkable, and also this symmetry is related to dualities in supergravity, so it's really useful in applications to physics. But if you continue to E8, you don't have this symmetry anymore, and you don't really get the Lie superalgebra that you would expect, or that would be useful in these applications to physics. But instead, you can use what is called a tensor hierarchy algebra, which is Lie superalgebra defined from the Dinkin diagram, so from any G and lambda. But then it's defined in a completely different way. It's by generators and relations, similar to the usual Chevalier presentation. So you associate generators to the nodes, and then there are relations that are similar to the usual ones. And then you get what is called a tensor hierarchy algebra. So it coincides with this Cartanification up to r equals to 7 in this E series. And more generally, they coincide when lambda is a fundamental weight of G for which the corresponding Coxeter label is equal to 1. But in other cases, they don't agree, and it seems that it's really the tensor hierarchy algebra, one as is now, which is now defined by generators and relations. This is the correct one in some sense. So I think it is this Cartanification that has to be improved. So what I I think what I presented for you is not really the full story. So this construction, it's a bit naive in some sense and has to be improved. So let me just also end with some words about the motivation from physics. So as I said, these tensor hierarchy algebras, they have been used in physics in an approach to supergravity, which is known as extended geometry, where you extend concepts in differential geometry and try to describe extensions of ordinary gravity in this way. So in particular, diffeomorphism, you generalize to generalized diffeomorphisms which unify the ordinary ones with gauge transformations that you get for the additional gauge fields that you have to add in supergravity when you add supersymmetry to gravity. And also this E series is the most interesting one. So in this case, you talk about exceptional geometry. If you take D series, you get what is called double geometry. And if you have A series, then it's just ordinary geometry. So this ADE correspond to these different types of extended geometry. And the E series is of particular interest since that corresponds to maximal supergravity. You have a maximal amount of supersymmetry. And there ER is a global symmetry of the maximal supergravity theory in 11 minus R space-time dimensions. So let me end also with some questions. Well, I mentioned this already. So we saw that we could construct a Weil algebra, or in the case of a consistent Z-grading, a Clifford algebra, in this A case by factoring out an ideal from this B gamma. So my question here is this a proper ideal also in general, and can we factor it out and get some generalized Weil or Clifford algebra? And that would also give something like generalized differential forms in the sense of extended geometry. So it would fit into that picture. And also, I mean, there are also some kind of vector fields used in extended geometry, which are also some generalized vector fields in some sense. Can they be understood in a similar way? And in particular, we have a section constraint on all the fields and functions in extended geometry, and it's the same representations that appear there. I mean, you have, so the coordinates live in B minus 1 if you take the corresponding extended geometry, and then you have a section constraint saying that if you take two derivatives and project them on this representation B minus 2, then you get 0. So this should be related in some sense, and that's, I think, at least I don't understand yet exactly how. And then, as I said before, this I think this cartonification needs to be improved so we can cover more general G. I think it's a nice construction because it's if you just have something by generators and relations, it's difficult to know if the ideal generated by the relations is proper or not. But here you see that you get something, but it needs to be improved, and also for the cases where G is infinite dimensional. For example, if you continue to E9, the affine extension of E8 and E10 and E11 and so on. So these are questions that I would like to get the answer to. Thank you.
Thank you, dear Jakob, for the great presentation. We will now proceed with questions, comments, and suggestions. Welcome, please. Any question? Okay. Thank you, dear Jakob. Is there anything? Is there anything you want to address or mention?
Maybe something. Well, I said here when G is infinite dimensional. So in this other construction by generators and relations, what is also interesting with these tensor hierarchy algebras is that you get something. So maybe let me go back to the. Yeah, I mean, if you look at this table again, so here you start with, in this special case described by the table, you start with E7 and so because E7 is 133 dimensional. But if you go to E9, E10, E11, which are infinite dimensional, then you get at degree 0 not only the ER algebra itself, but you get something more than what you started with, because you have it doesn't, as you can see, it doesn't have this triangular decomposition, and it's also, you also have E and F generators, but you can take E and F corresponding to different nodes and get something non-zero. So that's the way you can produce some additional module at degree 0 that you didn't have from the beginning. So that's what makes these tensor hierarchy algebras both very interesting. I mean, you get this structure of extra modules, but of course also very complicated, because it's difficult to know when you are done, when you have everything at a given degree.
Thank you so much. Any question? Okay. Thank you, dear Jakob. Thank you.